So let's look at the discrete time Fourier transform. Now we've actually covered most of the work involved in this, so a lot of it's going to be a recap. So we start off with a discrete function of time, f of nt. So this is our f of nt here, and you can see I've chosen this one in particular as an even function. Now whenever we take this function of time and we multiply it by our e to the I omega t, now we note here that the surface e to the I omega t, it's actually e to the I omega nt because the t now is going to be discrete. But because this is an even function, it means that the sine part of this disappears and we're only left with the cosine part. So we've only drawn out the cosine surface here. So this is actually the cos I omega nt, and you can see here it's actually discrete in terms of time. So this is our time axis here. In the time axis there's only discrete values exist, but you can see in the frequency axis is still continuous, but the time axis is discrete. So in order to do this discrete time Fourier transform, we take our function f of nt and it's going to modulate the surface. So this here is going to multiply the surface, and we'll see that just in the next slide. And once it's multiplied the surface, then we're just going to be left with a whole load of cosine terms, and we add the cosine terms up in terms of the time axis. So we're going to add the cosine, we're going to add all these cosine terms up in this direction here, and when we add them all up, the height of them is going to give us the actual Fourier transform here. And you can see here that the Fourier transform, importantly, is actually going to be a continuous function because the omega axis is still continuous. Now another thing to note here is that whenever this here has modulated the surface, well, this surface is going to continue on for infinity in this direction and infinity in that direction. So it means that the output here, which is the discrete time Fourier transform, is going to be continuous, but it's also going to repeat because this surface here is going to continually repeat. So for example, the cosine term here is going to drop down, come back up, and it's going to come up and down continually, and it's going to do it continually in this direction. So it means that whenever we add in this direction here, we're going to get a term in the centre here, and once this surface has repeated again, we're going to get another one of these terms. So it's going to be periodic, and it will be periodic here as well. So that means that whenever we take this Fourier, the discrete time Fourier transform of this function, in the frequency domain, it's going to give us a periodic function. And that's going to be important for when we look at the idea of aliasing. So let's look at this modulation of the surface in a little bit more detail. So this is the same function that we had above. So this function f of nt, I can see it's an even function. Now what we've done, we've actually shown the surface, which is the cos omega nt surface, and it's been modulated. You can see the actual height of the surface has changed. So rather than being a flat surface all of height 1, so like from above, you can see it's just a surface of height 1, or a continuous height. When we come down here, the surface here actually changes and it's actually modulated. So it's actually coming up like this and coming down. So this function here is modulated that surface, and whenever we add up the values of all of these modulated cosines in this direction here, we're going to get the discrete time Fourier transform. And as I said, it's going to repeat because this surface is going to repeat in this direction and also in the negative direction as well. So along the frequency axis, the surface is going to repeat because all we have is just, in this instance here, repeating cosines. Now another thing to note here is that we can rewrite the actual function and we can simplify it. So we simplify the nomenclature. So the discrete time Fourier transform the f of nt, well, the value of t, if we normalize that to a value of 1, then we can just say that the number n will tell us the number of samples. So for example, we say here that t is normalized to 1, and we can just say that, say for example, there's 20 samples in that particular range of 1, which in effect would be 1 second. So it means that in order to define what's happening in this discrete function in the time axis, all we really need to know is this value n. So the index tells us which one of these pulses we're actually dealing with. So it means that the nt, well, the t will disappear here as well. So we'll simply be left with the discrete time Fourier transform. We'll have f of I omega equals the sum from n equals minus infinity to infinity of f of n times e to the I omega n. And this is the general kind of format that you would tend to see the discrete time Fourier transform written in. So now we've looked at the discrete time Fourier discrete time forward transform. Let's look at the inverse transform. Now before we do that, you can see roughly what's going to be happening here, because whenever we're looking at the inverse transform, you can see here that we only need to take one period of this. Okay, so this may be a continual function, but we only need to take it over one of the periods. So we'll get to that in the next slide. So let's look at the inverse discrete time Fourier transform. So we want to go from the frequency axis back to the time axis. So we want this function here to reconstitute the function that we have here. So we have our function f of I omega, and you can see that it's even and it's periodic. And we're going to take this function and we're going to multiply it by the e to the I omega t. But of course it's not t, it's now the discrete value of time, which is nt. Also, we've picked this particular function out because it's going to be an even function. So it means that the I sine omega t part of this e to the I omega nt disappears. So we're only left with the cos omega t part of it. And we're going to take this f of I omega, which is this function, the periodic function, and this here will now modulate the surface. Now it isn't actually shown here with it modulating the surface, this is still the previous one, so this is the forward transform modulating that surface. So if you can imagine now, what we're going to do is we can flatten the surface back down to the cos I n omega t, and then we can allow this function here now to modulate the surface. And then what we're going to do is integrate. Now we have to integrate with respect to omega because omega is a continuous function, so we won't be doing any summations in this direction, we'll be integrating. Now you can see here that what's going to happen is that whenever this this function here modulates this surface, it's going to modulate it continually all the way from minus infinite frequency to positive infinite frequency. So it's going to repeat this modulation all the way through, and we only need, in order to reconstitute this function in the time domain, we only need to integrate over just one of these periods. So if the period is omega s, we only need to integrate from plus omega s upon 2 to minus omega s upon 2. So in effect we're only looking at just this one part of the function here that we really need to modulate the surface, and then we just integrate over that one period. So whenever we integrate over that one period, it's going to reconstitute this function here. But we've got to work out what we're going to do with the limits. So we know now that we're going to be integrating from minus omega s upon 2 to omega s upon 2. So that's equivalent to integrating from 0 to omega s. Now there's one other thing that we need to take care of here, and that is that whenever we integrate in this direction here, we're going to still have the function here, which is a continuous function, and we need to change it into a discrete function. Now the normal Fourier transform, when we did the inverse transform, it would be given by the integral of, it would be multiplied by 1 upon 2 pi. So we'd actually have a 1 upon 2 pi here, but because now we're going to be changing from a continuous function of time to a discrete function of time, then we had to have the conversion factor. So the little conversion factor, which we've seen in a previous video, because we're using an area sampler, the conversion factor is going to be a multiplication by this factor t. So we're actually going to have here the t upon 2 pi. But the t upon 2 pi is the same as 1 upon omega s, because omega s is in fact 2 pi upon t. So the discrete time Fourier transforms are going to be given by f of nt equals 1 upon omega s, the integral from 0 to omega s of f of I omega e to the I omega nt by d omega. So finally, here we have the inverse discrete time Fourier transform. We've taken away the factor of t, it's been normalised to 1, and we've got the factor t out of here as well. So we're left with our f of n equals 1 upon omega s, the integral from 0 to omega s of f of I omega e to I omega n by d omega. And I've put next to the forward transform. So these are the two transforms that we've been working to derive. So let's go ahead and we'll have a look at the forward transform, and we'll do an analytic example, and we'll also have a look at it in Matlab. So let's look at finding the discrete time Fourier transform of this function here, f of nt equals a to the n u of nt. Now u of nt is a unit step, so it's only going to exist for values greater than 0, and we'll restrict this to mod a is less than 1. In fact, we'll restrict it even further and say that a has to be greater than 0, so a is greater than 0 and less than 1. So we work out the discrete time Laplace transform of our function. We multiply it by e to the minus I omega nt from n equals minus infinity to infinity, but this function here is equal to 1 whenever n is greater than 0. So this is equivalent to the sum from n equals 0 to infinity of ae to the minus I omega t, and we can take our factor of n out, and this here is a geometric series, and the sum of a geometric series of this form here is given as 1 upon 1 minus x, where our x in this case is ae to the minus I omega t. So it means that the discrete time Laplace Fourier transform of an u to the nt is going to be 1 upon 1 minus ae to the minus I omega t. So let's go ahead and we'll have a look at this graphically. So this is it plotted out in Matlab. I've done it in 3 dimensions here, so we've got the omega axis, we've got the imaginary axis and the real axis, so it is a complex function. And I've also shown the purely real axis, I've shown the purely imaginary axis, I've also shown the magnitude here and the phase. Now the magnitude looks similar to the real axis, but it's not, it's slightly different if you have a closer look at it. And the height here is given by 1 upon 1 minus a, and the height here above the line is given by 1 upon 1 plus a. Now this is our function here. Our value for t in this case is normalised to 1, and the value for a I've picked out as 0.3. So you've got access to this and you can have a look at it in Matlab. So this is it actually in Matlab, so you can see here that we can go ahead and we can take the 3-dimensional function here, and if we turn it round we can produce the purely imaginary plot, and you can produce the purely real plot by turning it to the real axis. Okay, so that gives us the real and the imaginary, and then from the real and imaginary we can generate the magnitude. So we generate magnitude by taking the real squared plus imaginary squared and taking the square root. So it is in effect like drawing a line through the centre of this here and taking the line up to the point on this curve, and we get up to the point in this curve by taking the square of the imaginary plus the square of the real, and it gives us this line up to the curve. and all those lines are just set out in a single axis here, and that's the magnitude. And also we have then the magnitude and the phase here at the bottom. So that's us finished with the discrete time Fourier transform. In the next couple of videos we're going to look at something called aliasing. Now you can see the aliasing effect starting here, but we're not actually going to show it like this, but we can get an indication. We can see that this discrete time frequency, whenever discrete time signal, whenever we find the discrete time Fourier transform of it, we said that we're going to get a repeating signal or a periodic signal. But if the bandwidth, that is the frequency bandwidth of this signal here, is large, it means that this part of the signal here is going to impinge on this part of the signal here. You can see the crossovers and so on and so forth. You get these crossovers. So that would create a degradation of this signal, and it would mean that whenever we went to do the inverse transform, we wouldn't be able to reconstruct this signal. Now you maybe can't see it quite well for here, but over the next couple of videos we're going to introduce it in terms of convolution. So we're going to get this effect of aliasing due really to two facts. And one of the facts that we've already looked at, which is that if we have an impulse train in the time domain, it will give us an impulse train in the frequency domain. And also the second fact is that whenever we multiply two functions together in the time domain, it's equivalent to convolving them in the frequency domain. So we're going to look at that over the next video, and we'll see the idea of aliasing and how we can prevent it.